Use a stream bitrate of 2500K. Okay, there is a warning.
You're live already?
Yes, yeah, because it's too, there is a warning.
A warning that what?
Look, bitrate, whatever. Okay, I think we can start.
All right, welcome everybody. Can you hear me? Yes. I heard there were some sailors in the audience today. Yes? Who's a sailor? Who's been on a boat for a while? Yes, very good. So welcome to CERN, welcome to IdeaSquare. And I'm gonna explain a little bit shortly what we do here at IdeaSquare. And I'll try to stick a little bit with the boats because I think it is a bit of a fitting image. So, you know, at CERN, you can compare it a little bit to a regatta. We all have the same goal. We're all on our way. But sometimes we are a little bit isolated in little boats, so could say. And on a boat, you know, it can get heated. It is a hopefully very nice voyage. But sometimes you, after a few weeks, you wish to see somebody else. The boat is not the biggest usually. You wish to exchange ideas, talk to others, and, you know, get some fresh wind in your brain. And so we try to consider ourselves here at IdeaSquare, by the way, not because we like squared ideas, but because we like to be the space where people come together and exchange ideas, get inspired, and inspire others. So we like to see ourselves in this way as the harbor of IdeaSquare, the safe harbor where everybody can come with their crazy ideas and inspire others and put ideas into reality. By the way, I'm Ole. Hi. And this is Katerina.
I'm Katerina Batista, and together with Ole, we're two of the educational program coordinators. So part of our activities as a harbor, as a safe harbor, have to do with making ideas become a reality. So we have different...
The mic of Katerina doesn't work.
I will maybe start again. Hi, I'm Katerina Batista, and as one of the educational program coordinators together with Ole and other colleagues as well, we're taking care of different programs that bring students from all over the world together to IdeaSquare. And part of what we do here at IdeaSquare is to, another little change, is to help and create the conditions in which different ideas can become a reality, can become real and tangible. So you can see that through the different prototyping facilities that you will see around you if you have a look around. You might be able to see some very crazy looking experiments from people at CERN, also prototyping for their own collaborations and their own experiments that need certain components. And for most of the time, what we host here at IdeaSquare are the student programs that we are involved with. And in which, in these programs, what we are focused on is really trying to translate the lessons learned from CERN, how CERN people work together with people from different cultures, different disciplines, working together towards a common goal, and being able to really challenge certain paradigms and always be at the frontier of science and of innovation. So we hope that the students that visit us get inspired with the same mindset and the same values and work together towards common good, towards the common good. And so to do this, we developed a new approach in which we call IdeaSquare Planet. And we take students figuratively, of course, in a thought experiment to a new planet, completely empty. And we challenge them to think, how would they organize society all over from scratch? What would they do differently? And from this thought experiment, we hope to translate and be able to apply some of these learnings when we come back to Earth and when we try to tackle real world challenges and being able to bring a fresh perspective, fresh ideas that come from these different thought experiments that really allow us to have a blank canvas to imagine and to question what if we would do things in a different way. And so this, I feel, also captures the essence of IdeaSquare, which is to question what if, to imagine together, to follow our curiosity, and as we always say to our students, to have a license to dream. So hopefully you can also embody that experience here today, and together we can also have the chance to ideate and to have beautiful discussions together. So welcome and enjoy.
Thank you, Rita and Ole, for this welcome to this special space at CERN, where you can enter without any badge except the one for the event today. So the event today, Citizen Science and AI to Combat Plastic Pollution, is an official side event of the INC-5, the United Nations Plastic Treaty negotiations ongoing right now in Geneva. I'm particularly grateful to United Nations Environmental Programme Geneva and the Geneva Environmental Hub for hosting us in the official program. I'll just introduce very quickly the plan for today. So this is the official calendar. You can see we are in it, and thank you everybody for coming. Thanks also for the people who are following us live on YouTube. The program today, we have heard from Ole and Katarina a few words of welcome on IdeaSquare, the space we are here right now. I will present the Polarquest Association, which I chair, and is at the origin of the idea of holding this event, together with colleagues from CERN who are working on developing AI for teaching satellites to spot plastic from space, especially along the coasts and in the sea. But before hearing from them, we will hear from an expert, a world expert in the marine plastic problem, who was also a member of the negotiations on the plastic treaty in Busan, in Korea, and is joining us on Zoom. This is Stefano Aliani. He's one of the scientists in the Polarquest team as well. Then we will hear from another Polarquest member, Rosy Mondardini, who's sitting here on the first row. She's a citizen science expert from ETHZ Zurich and also collaborating in the Polarquest core team. And finally, the big scientific presentation from Sioni Summer, who is here, and he will speak about this project, SpAIce. And in the end, we'll have a coffee together in the kitchen of this space, and afterwards at 5 o'clock, 5:10, we go to do visits of the CERN campus, 2 areas that are accessible. Right now we are colliding under our feet, 100 meters below ground. There's the LHC colliding protons, 40 million times per second, studying the Big Bang and the universe at its origin. So we cannot go underground. You can come underground in the winter if you come back to Geneva, for those of you who are not from the region, or our next open days, but we will visit on the surface 2 specific areas that are not far away on the campus and can be reached on foot. At the end of each presentation, we will have time for 1 or 2 really burning questions, because we need to keep the timing, especially to be able to go on the visit. But we will have the networking time over coffee for developing more on every subject that you will have heard about. So let me start with Polarquest and how this association was born. This association was born in 2018. We had a specific mission in mind. I am a science journalist, not just a science communicator at CERN. I also do science journalism outside, and I went to the Antarctica and to the Arctic, and I realized how important these polar areas are for our planet. So after a couple of reportages, these extreme but very beautiful regions, I decided to put together a citizen science association to involve citizens in the research done in the Arctic. And we have done various expeditions. The most iconic and the most important one was in 2018, on the 90th anniversary of a historical expedition to the Arctic, the one by Umberto Nobile and the Italia airship in 1928. So we redid the same sort of science with the instruments of today, involving students, using a sailboat to go to the Arctic. And even though it was a low cost, in between inverted comma, compared to institutional Arctic expedition, low impact because it was on a sailboat, completely ecological, without heating, and without the basic, just a really basic sailboat, 10 people on board, 5 women, 5 men, a lot of young people involved in various legs, but also following us, building the instruments, analyzing the data. These are the highlights of the expedition. So we did, first of all, since we started with sailing, we are one of the very few sailboats who did a complete circumnavigation of the whole of the Svalbard archipelago, which is the northernmost inhabited land on the planet, and we reached the 82nd parallel. We did there detailed studies of microplastic in the sea and macroplastic pollution on the very remote beaches of the Spitsbergen, including we measured microplastic at the record latitude beyond the 82nd parallel. This is also a world first sea level cosmic radiation study. I won't talk about that. This is a study similar to what the LHC does underground under our feet, but with real particles coming from the cosmos that at the poles are more intense because of the magnetic poles, and these are charged particles. We also did the first 3D mapping of the northern coast of Svalbard, and we were the first to visit the crash spot of Airship Italia, where they sent the first SOS. So in this presentation, I will mostly concentrate on the plastic. This is the itinerary. So we left from Iceland. We crossed first a little stop in Greenland, a couple of hours. Then we crossed the Atlantic, northern Atlantic, to Svalbard, circumnavigated, and reached the northernmost point of 8207. And then we went back to Longyearbyen all around. This is an image of the boat in ice. It was an aluminum boat, especially built for the Arctic. If you go in the Mediterranean with this, you will have a sauna inside, because it's insulated passively, but no heating, no fossil fuel emission, solar panel, wind power, and so forth. And this is when we crossed to uncharted territory. This is what you see on the plotter. For sailor, this is a especially emotional moment. It could be good emotions like I'm excited to do it, or I'm very afraid because we go into uncharted territory with a sailboat. And this is the polar ice shelf, which we found on the 82nd parallel north, which is extremely high latitude. Usually the north coast of Svalbard is locked in ice. This time, no. We didn't see ice until we did 100 miles, nautical miles, north of the northernmost spot of the archipelago. And what we found on the beaches, you can see it's an uninhabited area. There are only polar bears living here. It's very far from the research centers and the administrative capital. This is the northeastern coast of Svalbard, where there is nothing, nobody living. Very few people get there because usually it's locked in ice. And we found a lot of plastic. The most visible you can see from fishing nets, but we also found this kind of tanks. This was especially interesting because it had the bite of a polar bear plus a text made in Italy. So which means that obviously the plastic that reaches those coasts does not come locally, because the polar bears don't make or produce or consume plastic, but it comes from us through the marine currents that are like conveyor belts that bring all our pollution to the Arctic especially. More images. These are reindeer's antlers that are caught in a fishing net made of plastic again. And we could also see many corpses of wild fauna, local wild fauna, dead because of plastic on land. Now, in the sea, we had citizen science because we involved 2 high school girls who had nothing to do, not even an idea to study science afterwards. One of them is following us, Safiria. She's a member of Polarquest still, and she's studying marine biology in Australia right now. At the time, she was 18. And she learned how to use a manta net to sample microplastic all along our voyage. And here you can see a little video of how we sampled. So it's a manta net that you troll behind the boat at very slow speed. This is the ice shelf. And on the ice shelf, we found a piece of macroplastic visible to the naked eyes in the net that we trolled at the edge of the ice shelf, which is just a premonition sign of what we would discover afterwards, because if you look at these results that were by the way, carried out at the laboratory of Stefano Aliani, the National Research Council Marine Institute in La Spezia in Italy, ISMAR, where he's a research director. He supervised one of our students who just had her bachelor in biology. She analyzed our samples, and these are the samples just on Svalbard. We also sampled all the way in Greenland and also back to Norway. But these are just the trawls that we did around Svalbard. And the Manta 4 is this one. And it had the highest content of microplastic. This is explained, Stefano can explain better than me, by the marine currents that bring all the plastic and they sort of hit the ice shelf and they somehow accumulate there, where the damage is bigger, because there you have ice and it's influenced by the plastic. You have also a lot of marine life, and you have the base of the food chain that is threatened by this content of microplastic that never disappears. In spite of being a citizen science expedition that I put together with the fundraising plus obviously the support, especially from the point of view of training of the people and analysis of the data of sseveral marine and scientific institutions in Europe. But in spite of this being done by citizens, we got a publication by Springer that you can see there. That presented our results. Another project I wanted to talk about is the drone mapping project that we did during that expedition and also some other expeditions that followed. Gianluca Casagrande is with us on Zoom from the European University Geography Lab of Rome, the GREAL, and he was the head of this project. This is also citizen science because we used commercial drones and open source software that was prepared by students of Gianluca at the laboratory in Rome. And this, you can see the drone that we used. Here you can see that with the drone, initially we took them for 3D mapping, but also because we were shooting a documentary on board and the images from a boat, in the boat, or of the landscape are not grandiose like a drone can do. So these were the original uses of the drone. These are Gianluca's slides. I will go quite fast on them, but if there are any questions, we can ask questions to Gianluca. Basically, in a short summary, we used commercial drones. There are 3 categories of drone: open, specific, and certified. Certified are the ones that are used by big companies like Leonardo and so on. They need a lot of permissions. We used drones that you can buy in a toy shop, essentially, but with the software prepared by the university students. The drones were capable of acquiring high-resolution images and also sending externally low-resolution images so that we could use them immediately also for communications. What we did for 3D mapping, a series of what you call orthophotos, that can be at the same time used for photography, but also after analysis with a specific software, they can give you a 3D rendering. So you have 2 types of rendering from the photos. And we use them to improve the maps of Svalbard, the geographical maps, and also the sea charts, because believe it or not, in an era where we know a lot about the solar system and the planets in the solar system, we know still very little, especially in 2018, about the northern coast of Svalbard. The charts and the depth values were very wrong. We corrected some depth values by 150 meters. There was an error because, of course, with a lot of calving of the glaciers, the sea bottom changes a lot. So we improved the maps of the coast, northeast coast of Svalbard and northern coast of Svalbard using this drone mapping. But in the end, we also realized that with the same system, a posteriori, we could do an analysis of the macroplastic on board. And the special case is this Alpini Oia, the island of the Alpini. The Alpini Corps in Italy in 1929 went to look for the missing people from the expedition of Nobile. And they named this island because it didn't have a name. They actually discovered it. We went on this island. You can see from the drone photo, we are here, this is our tender, and we are here. But, and on the right, you can see the mapping that was done. This is also a photo of the same spot from land. But we also realized that we could identify macroplastic of the size, minimum size of 30 centimeters, not below that. And we ran the software, and we also did some ground routing. This is a fishing net identified from the software. And we could identify objects like these that were all over Alpinioia, a place where basically after 1929, very few humans visited. But still, we could do a mapping of the plastic present on the island, above 30 centimeters, and this is the mapping. So this is also a publication that came up from a complete citizen science project. Maybe we can have Gianluca on Zoom for a few questions on this part, if you are curious about any scientific questions. Or Gianluca, can you hear us?
Yes, I do. Good afternoon, everybody.
And we hear you loud and clear. Maybe you can put also the Zoom screen. Thank you. This is Gianluca Casagrande, European University of Rome, Geographical Lab, but also Italian Geographical Society, so a geographer who uses advanced methods for geography. Maybe, I don't know, Gianluca, if you want to add anything very important that I missed on the very short summary of your slides.
No, we're very basically I think we have validated pretty well the possibility of using very low cost off-the-shelf equipment for this kind of survey, especially for macroplastics. And these things are very, very effective because once you establish pretty simple but thorough protocols, then the fact that these technologies are available to virtually any generic customer enables many citizen science groups all over the world to use them according to standard de facto for portability and also according to, I would say, validated protocols, so that research can gather data from many more sources than in the past. And this provides scientific research in general with many more data to process to get a better and more comprehensive view of phenomena. So this is a formula that we were very satisfied with because we believe it works well, and it's very easy to deploy. So we definitely want to go along this line in the future as well. And I'm here if there is any question about this.
Yes, if there are any questions. For Gianluca, I just want to underline that data from the sea are missing. The sea is enormous, it's 89% of our planet, and is also in 3D because there is the depth as well. And it is not completely false to say that we know the interstellar space between us and the last planet of the solar system. Then we know our sea and our ocean. And yet the ocean is the source of life, and is also the place where life has its start. The food chain starts from phytoplankton and zooplankton, then you go to the large mammals that are in the sea and us. And if that is threatened, and if we don't tackle the problem scientifically by understanding what is happening there and how to intervene and what's the most efficient way to intervene, then it's really stupid not to do it. And citizen science can have a big role in the mapping of the sea and providing data from the oceans. Okay, so maybe I can continue with the presentation. I just wanted to, I have the last two slides on Polarquest today. So this is the original team that at the end of the first expedition around Svalbard, when we arrived, very happy for the results. Some of the team members are present here. Maybe I already mentioned Rosy, she's here. Mike is there, drone pilot and technical coordinator. Online, we have Kevin Monroe. Can we have the Zoom just to say hi to Kevin? Gianluca, of course, you met. He's one of the original members. Kevin is there. He's also previously an engineer at CERN, now working in Italy, but a diver and committed to the environmental cause as each of us. He can dive in the Arctic under any circumstances, including swimming with polar bears. And he's an amazing member of the team. And then, I don't know if Safiria is connected, but she's connecting from Scotland. She lives on a sailboat and studies marine biology. When she came with us, she came from classical studies at high school, and she's completely conquered to the cause. Then the team today includes, let me see if I can go on our website, polarquest.org. the team today includes also many other contributors. We divide them in core team, those who work to make this happen almost on a daily basis. We all have other jobs as well, obviously. This is our volunteer jobs. Then we have young scientists that work with us. Sorry, can we see the screen of the slides? Thank you for telling me. Can you? I moved online from my slides. I can see them on the computer, but not. Okay, if this doesn't work, it's not a problem. You could do it? Okay. Hi, you have a question? Then can you give him the microphone, please? Can you say who you are and for whom the question is, if you have somebody in particular? Yeah, you're... Okay, so this is a question for Gianluca, so sorry, back to Zoom. Yes, Gianluca, did you hear the question?
No.
So what software did you use? Does it need extra coding, or is it ready, available for use, right?
No, as far as drones are concerned, we did not need any further software scripting. It was, well, we used several drones. The one we used the most was DJI Phantom 4 Pro. We had several examples of those, and we also used, I think, a Mavic Air, and and also a Mavic Mini, if I remember correctly. The difference was that we tended to use additional payloads when needed. For instance, the Phantom 4 was also used. It already has a built-in visible light RGB camera. We used sometimes an additional payloads with a near-infrared camera.
Gianluca, the question was about software for analysis, data analysis.
Software for analysis, we basically use open source software. The only commercial one we used for photogrammetry, and it was either Agisoft Metashape or Agisoft Photoscan. In all other cases, we used the normal open source software. And the few measurements we made with NDVI maps, we used Infragram, which was an online platform.
Okay, thank you, Gianluca.
QuantumGIS mostly. QuantumGIS and the plugins for that software.
Thanks. Thank you very much. I saw that Safiria was connected. Can we go back to the Zoom? Maybe she can say hi from where she is. Gallery, yes. There she is. Hi, Safiria.
Hi, everyone.
Where are you connecting from?
I am connecting from Stroma.
There's a sound in the background. I don't know what it is. Never mind. We saw you. We'll talk later. Thank you. Okay, so back to the slides. The team we have seen. So recently, I created a fleet for science of similar sailboats, so a small sailing yacht that you can see here. And they are all part of our network of sailboats that coordinated by us, who make the contact with the scientists, and also we give input, create communication projects. We can essentially put ourselves at the service of scientific institutions who want to give an experience to young scientists who cannot access the institutional expeditions and need to practice on the field with our sailboats. You can see a few here. We have sailboats that cover all the oceans, and this is just starting. And voila, this is a call for scientific institutions who want data. We have the expertise not only to collect data, to train young scientists on the marine sampling, but also to communicate about it and propose citizen science projects. And that's it for polarquest.org. You can follow us on these social channels and on our website. And now I'm ready to give the floor to the second presentation, which is from Stefano Aliani. So we need to go on Zoom. He will share his presentation on Zoom. As I said before, Stefano Aliani is a marine biologist and oceanographer, research director at the Marine Institute of the Italian National Research Council in La Spezia in Italy. He's also member of various international Arctic and Antarctic committees. We met on an oceanography ship going to Antarctica together long ago, where I was a science journalist and he was leading some research. And of the most important information I want to give about Stefano, not only is one of the scientists of Polarquest, but he has been part of the negotiations for the plastic treaty in Busan in Korea. So he can give us a perspective of an insider about what science can do for the plastic treaty and what science should be doing for the plastic treaty. Stefano, the floor is yours.
Can you hear me and see my slides?
We can see you and hear you loud and clear, but not the slides. Have you shared them? So Stefano is connecting from La Spezia.
Let me try. Well, can you see the slides now?
No.
I love this stuff.
We could see them during the rehearsal, obviously.
Yes, of course. When we did a try, it was working. Again, from scratch. Sorry for this. Zoom again. Share. Sorry for this. Go to desktop number 1. Share, can you see it?
Yes.
Okay. Let's start from. Again, the captions, I love it.
Yeah, the captions are there.
Yeah, I removed
Again.
many times. I always remove them, but back every time. Okay, how can I remove them? Okay.
They're removed.
Yeah, gone. We did it.
Good.
Hi, great to see you, even if I don't see you at all. How your day is going well, and this is just after the dinner talk.
Can you speak louder?
So I have to. Yes, of course. So I have to dive into something inspiring for you today. The topic I'm gonna speak about is nothing new for some of you, and it's new stuff for others. Nevertheless, even if it's not new for some of you, I hope it's a good chance to focus and exchange ideas about this topic of plastic pollution and science. So let's start from scratch. I don't know how to go further. Okay. Definition of plastics. Well, I will not give you any definition of plastic. You say why? Because there is a lot of debate in the treaty about what plastic is. So any definition that is given now, it's could be changed after the agreements in the treaty. So I will talk to you about polymers, which are the chemical class of materials that make up all modern plastics. You know what they are? Molecules consisting of a chain of repeating small molecules, monomers. Easy for a place like CERN to talk about what the polymer is. Maybe someone in the group is not aware of this. So no definition. So I start to talk to you about the rise of the plastic pollution problem. The plastic rise was invented, or let's say the early plastic was made in the 18th century by Alexander Parks, and then celluloid by John Hyland. And you see on the pictures on the right, you see celluloid materials. Those are films used for cinema, old-time cinema. So plastic was fundamental for the development of cinema. Or on top, you see the writing tool you are very familiar with, that is made of plastic. On the left, you have an image of what pens were before plastic. So for any item we use today, there was an item, or in many instances, there was an item that was made for another material that was not plastic. Then we have synthetic plastics. Bakelite is the first one. You see on the right that the bakelite is thermostatic resin that has insulation properties and was fundamental for the development of electricity. So plastic was very important. And then the word plastic expanded, especially immediately before the last World War II and immediately after. So we moved from tubes, for instance, made of metals to tube made of PVC. And then we have other polymers like polyethylene and nylon. And now we use, from big tubes, we arrive to very small tubes, like the straws you see there, that is still made of plastics. So we move the problem from the solution to something that didn't exist, the straws. And so new things came in our lives that didn't exist before, made of other materials. Innovation continued, and then we have polystyrene, Teflon, ABS, and more. We have a lot of them. In some instances, we all knew these styrene chips for packaging, or the packaging for food. Of course, for food, there is the non-plastic alternative, you see on the left. There is also a non-plastic alternative for styrene chips that is made of cardboard. So, slowly, or maybe in 15 years, if you want, or 60, plastic became ubiquitous in modern life. Everything from packages to medical devices include plastics. And research continues to explore new materials, including biodegradable plastics and new polymers. What you see in this, in this book, this is a book, Plastic in Medical Devices. There is a series of these handbooks who explain how to manage plastics dedicated to medical device. This because plastics has medical effects. So doctors who has to manage plastics items has to follow certain rules. Modern plastic, that's something that is going on now in the new plastic. Polymer science is running fast. We have recently this paper from Nature is from Science, sorry, is from November 24. Molecular polymerization, which means we are not talking about the standard linkage between atoms, but we use a different kind of linkages, which has a completely new, opening completely new chances or world in polymer science. Then there are biopolymers. Biopolymers are divided in bio-based and biodegradable. There is discussion about that. I don't go into details. What is bio-based and biodegradables, maybe I can tell you later. But there is a big difference, but often the same name is used, biopolymers, meaning two different things. Bio-based means that comes from biological carbon. Biodegradable means that may came from any carbon source, but can be degraded by biological activities. And then we have self-healing polymers. self-healing polymers are polymers, new generation of polymers that can repair themselves if they are broken. That's very interesting property. Absolutely, yes. And for the chemical and polymer science, yes. For the technology, material technology, yes. For the environmental point of view, I'm not sure. Depends on the way they repair the damage. If the chemicals in the environment are incorporated into the chemicals, into the healing polymers, and remains there, probably there are sponges for the self-healing polymers are sponges for environmental pollutants. So the question is necessary to assess environmental impact of polymers. We have to know what we are releasing in the environment, even if it's small quantities, and we actually don't know it. The other way around is, for the point of view of general management, do we need simple polymers to facilitate waste management and recycling? That's a good question to be addressed in the years to come. Well, why is plastic becoming a problem? The main problem with plastic is that it's not biodegradable, apart from the bioplastic, a subset of bioplastic, as we said. And there is a discussion also about whether it's actually biodegradable in the environment. And so plastic doesn't rot like paper or food, and can run in the environment for hundreds of years or for endless time. And each year, million tons of plastic is produced. 50% is single use. So we are releasing in the environment something that is done for last forever. And we use the logic, take the item, make the plastic, and dispose it. It's a line. So the linear make, dispose model dominates the plastic life cycle. So we create vast quantities of single-use plastics used for a very short time, sometimes minutes or seconds, and then we discard them, which lead to a massive waste problem. Because waste is not is part of the system, even if we reject waste is part of the systems. And plastic pollution, or plastic waste in this case, alter habitats and natural processes, reduce ecosystem ability to adapt to climate change, directly affect the people's life, food production capability, social well-being, and human health. This is a unique statement. So we are starting talking about citizen science. I will not go deep into that. Just a few words about citizen science because it's important, because citizens are important players in the solution of the problem. I just mentioned what is the very first action involving citizens and plastic, to my knowledge. Maybe there is something I don't know, but that's what I know. This non-profit organization, Keep America Beautiful, in December 1953, funded by American can company, glass company, Coca-Cola and Pepsi, create a series of advertisements to end littering, improve recycling, and to beautify American communities. It's the very first attempt to activate a cleanup program. The organization focus was on littering and recycling, and has been criticized as greenwashing, that diverts responsibility away from corporations and industries. Of course, there is a possibility of greenwashing. No matter discussion about greenwashing, it is not relevant. It is now relevant for us that in 1953 companies were aware of the waste problem and called for community education. And that's quite important. They also gave the name of litter bug to a person who tends to drop litter and do not clean up. The art shift, that's a word that is not used so much anymore, but it was created in that time by this group or people related to this group. The point of this advertising, and it shifted the focus for pollution prevention from the plastic producer to the consumers. It is impossible for people without education and facilities to prevent pollution. Because you need facilities, you need education, you need bins to put your rubbish. If there are no bins, there is no chance to stop this. So it's not a consumer problem only. So citizen science rise quite fast recently. I just grabbed some random images from the web. There is just random, so no comments about that. Some of them are good activities, are positive. Some of them are likely greenwashing. There is a risk of greenwashing in citizen science activities, but not all of them are like that. So what science did, we see the rise of plastic pollution or plastic production on blue on the graph with time, and we see the rise of papers, number of papers on the topic with time. The growth rate of papers on a new field follows some equations that are well known. And at the beginning, let's say until 2010, 2012, the growth rate of papers on plastic pollution just followed the equation, you know, the standard growth rate of papers on a new topic. Then there was a boost. And now there is a lot of knowledge, much more knowledge. We knew things faster than any other fields before because of this impressive growth rate of the number of publications. So we are able to make prediction of risk, inform the development of long-term solution and mitigations in a time that is really, really short. Nevertheless, even if science is still growing, there is enough evidence to suggest immediate and widespread actions to be taken just now. The first plastic fragments were found in the continuous plankton recorder samples dating back to 1960. There has been a reanalysis of samples, plankton samples from the 60s, published by the Plymouth Marine Laboratory recently, and they found plastic in the 60s, microplastic in the water of the 60s. And the time series revealed that the increase of plastic particle density positively correlated with the global plastic production trends, which means the plastic production increased, the particle density in the water increases. In the 80s, that is 30 years after plastic mass production, evidence the problem of plastic to the environment and people was clear. So just in the picture on the right, you see some sources and some impacts for the environment and some socio-political dynamics. What scientists did, they included plastic as an essential ocean variable. Essential ocean variables are variables that are fundamental for describing the functioning of the ocean. Some of them are temperature, plankton, or color, or altimetry, or many other variables. Plastic has been presented to the Global Ocean Observing System Steering Committee to be included as fundamental essential ocean variable. So, what can do science for this? Well, let's start with the value chain of the science marine debris observations, or if you want, what can science do for to support the treaty against plastic pollution. We start from the basis. There is no, in this hierarchy, there is no level of importance. It's just a graphical layout. Any step is equal relevant. But let's start from the bottom. We have observation of the ocean, so we need data. We can have with Manta, with drones, as we said, with satellite, with any tool. So we have collection of data. Then we have organization of data. So the data are organized in databases. I can show there is a database, important database in Japan. There is an important database in Europe. There is an important database at NOAA in the US and many others, and in Australia. When you have data and databases, it's time for modeling. Modeling means physical modeling and theoretical modeling and economical modeling, for instance. And then there is the modeling part, which is obviously a science, modeling science and so on. After that, we go into the reporting part. This reporting part is often done by UN, for instance, by some environmental organization like WWF or any high-level experts on reporting. And those reports are the meat the treaty uses. You know, the people in the treaty do not read papers, they read the reports. So that's the value chain. And policymakers read this summary, this review, this kind of reports done by this organization. And this is the way it works. So people in the treaty are expected to be educated. And the way to educate through science is this way. There is a lot of people, a lot of effort in this direction. And some example of science, this is a time series, model of time series of plastic pollution over time. And you see different scenarios like business as usual, collect and disposal scenarios, and recycling scenario, reduce substitute scenario, and system change scenarios. These are all published in Science. These are all forecasting models to explain what happens to plastic pollution. This is the cost of the different scenarios, cumulative cost. We are talking about billions of US dollar at the value of 2018. The graphs, the models considers, of course, all the economic situation. So you see that the different scenarios may cost a lot of money to taxpayers. So, and I'm going to finish, is this slide shows there is a deep knowledge of the problem and the good scientific agreement across different science communities and across disciplines about science as a fundamental support to policymakers. A call to governments to get advantage of available knowledge and to consider scientific evidence is a challenge for this treaty. Making an agreement now that are in line with science will mitigate health and environmental impact, and any influence of this treaty on the planet will be terrific. What is the scientific community, in particular the International Science Council, wrote some statements presented at the INC-5 treaty. These are some of the aspects. So first topic is the treaty should consider the upstream plastic production to end plastic pollution, so get a target on the production of primary plastic polymers, new plastic polymers. We have to learn and focus on a list of chemicals of concern and products, just like, as I said, self-healing polymers, but also additives like bisphenol or chemicals that may damage the endocrine system of people and animals. And then we need to use science to monitor with a robust scientific monitoring approach, using what already exists, for instance, the marine debris observing system. So no need to do something that already exists and to implement into the system. And then create a robust science policy society interface that is called SpAIce. That is based on this science policy interface, is based on the value chain that I've shown you before. So these are the details where the science can take action to support science-based treaty, and the articles of the treaty where science can actually take active actions. Then I introduce you the Sciences Coalition. It's a coalition of 450 independent experts from 65 countries concerned about the misinterpretation of science by some results in the treaty. And their work in the treaty is to check that science is not misinterpreted or misinterpreted in the scientist treaty, which is not necessarily something done on purpose, not necessarily ugly people who's doing that. Simply, they don't know, so they need to be supported in this way. Whatever we do, whatever the achievement of the treaty, whatever they do, this is once in a planet opportunity to end plastic pollution, and what we do doesn't affect how the planet works. So the other organization who sent a statement to the Plastic Treaty is the World Health Organization, and they say that the negotiation should be three principles: highest attainable standard for human and environmental health, potential and risk of exposure associated with plastic polymers, chemicals, at all stages of plastic life, ensure access to safe and effective end products, which means have the proper polymers management, as I show you in the books at the beginning. And other organizations and stakeholders interested in signing a statement highlighting the role of science in the treaty are ongoing. A new statement will be prepared and circulated soon for scientists to sign it if they agree on the topic. I would like to thank you all for listening, and all parties involved in the negotiation for the effort we are doing to fix this huge problem. That's all for now.
Thank you, Stefano. This was extremely effective. We have probably time for one question. Can we show Stefano's face on the screen? There you are. Thank you very much. Any question? What I can say is that we will help you distribute the statement in one of the temples of science where we are broadcasting right now. There's a question here. 1 second, the microphone. Is it on? Okay. Can you say your name and also?
My name is Riyad Bazia. I'm an environmentalist. I'm working with the international organizations here in Geneva. Thank you very much for your presentation. I really appreciate. A coalition for scientific, 450 independent experts from 65 countries, and they are here. Yeah, very good. But can you tell us what is the future of your coalition as a scientific association or organization, or if you are expecting being more involved in this issue, whether in international level or and there is also expert in this field that can support you. Thank you.
Thanks.
Well, I don't know. That's a basic question. I don't know because it's a volunteer-based organization. At present, is funded by scientists with their own science money. This is a big problem because, for instance, other organizations, other lobbies are well funded by big companies. So the number of scientists that can go on keeping the pressure on this topic, I would expect will reduce. Nevertheless, I'm sure that the kind of follow-up of this scientist coalition there will be, I don't know exactly how and where, especially if the treaty will consider what is said and will create this science to policy interface as in the plans. So there will be this chance to create more than one probably organization or institution or whatever they will decide to create this interface. There are different chances. One is a community of parties, as for climate, where there is a science policy interface, or other kind of diplomatic solution. I don't know what they will decide, so I cannot answer your question. Actually, depends on exactly on what they will decide in the treaty. For sure, the group of scientists will stay close.
One more?
Anyway, it's better, yes, to implement that as organization or international associations, and it could work in parallel with politicians, with diplomatic area. You are scientific, it could be because you are anyway civil society activist and you are providing scientific solutions, scientific data. It will be better keeping a coalition of scientific like that, and the Congress yearly or every 2 years or anyway. And thank you very much.
Yeah, if I may answer, yes, I definitely agree with you. The critical point is which tools will came up from the treaty to do that. There are different instruments that can be done, and we don't know which one will be decided. So we just have to stand by and start working when we know better what will the future of this interface will be.
Thank you very much, Stefano. It's time to move on to the next presentation. We are going into the core of the matter today. The title today is Citizen Science and AI to Combat Plastic Pollution. Let's start with citizen science into the depth of it with a top expert, Rosy Mondardini, who is Director of Research and Development at Citizen Science Zurich, both university and ETH, and also Polarquest member. Thank you, Rosy.
Thank you. So by now, you have heard, well, first of all, yes, I'm Rosy. I'm from Citizen Science Zurich. This is a competence center created by the University of Zurich and ETH Zurich about citizen science, and also a member of Polarquest. So you have heard about citizen science a lot by now. So I think this small presentation is really to make sure that we are on the same page and that we understand what we are talking about when we talk about citizen science. So this is the definition of the Oxford Dictionary. So is the involvement of non-professional volunteers that we call citizens, but has nothing to do with citizenship. It's really a way of like calling the general public into the scientific research process. If you look on the web, if you Google it, you find other definitions, actually all very similar. I really like this one. Is a broad range of activities where people produce scientific knowledge outside of academia. And this really broad range of activities, there is not one way of doing citizen science. There is not one activity, one project. There are many, a range of them. But they all have, very specific goals. And actually, there are also different names. You may have heard about community science, community-driven research, science 2.0. There are many ways of calling the same kind of activities. And this definition also I like because highlights also another aspect, that is that the general public is engaged in an active way. And here I always say the same example, a survey is not citizen science, or at least there are exceptions, but with a survey, it's like a passive collection of information about the person, so the person is the object of the research and not the subject. So Active engagement in practice means that here is like a statistic that was done in June 2021. About 750,000 people every month are engaged in some kind of activities. They may be collecting data with their smartphones or collecting data with sensor, do-it-yourself sensor or local sensors, or they may be analyzing images or documents. They may be donating the spare time of their computers. We'll say something more about this. Or, you know, there are increasingly activities where citizens are involved at the very beginning of the research process that is really co-creating with scientists the whole research question, the whole project, the whole study. It is a form of crowdsourcing, obviously. However, it is there are some characteristics that makes it a very special kind of crowdsourcing. You cannot think about Amazon Mechanical Turk or this kind of brainless and repetitive activities. The first main difference is that the focus is scientific research. I will never stop repeating this. It's not science communication, it's not community engagement, it's research. We are trying to do research together. So that's the focus. And so the goal of this kind of project, since it's research, is to create some new scientific knowledge. Another aspect is that we mentioned that citizens or like non-expert, non-scientists are actively involved. And most of the times these activities have to do with data. Can be data collection, data analysis, but there is a part of active engagement. Can I have the slides back? And then one other aspect that is like very, very important, that is the projects are mutually beneficial for the two communities. So in citizen science project, the data that you obtain, the activity that you do is not only in the interest of the scientists that get their data and do their publication, they have to be equally for the benefit of the people participating. And usually this expressed in the form that you have data, the scientists use the data for their scientific publication, people use the data to advocate for change. So for policy making, for advocacy, for activities like that. If you want to know more, there are the 10 principles of citizen science by the European Citizen Science Association. You can look for that, and if you look at the principles and at the project, you can really see very quickly if it is citizen science or not. So there are many different projects, we said, many different activities. In a very general way, they can be grouped in three main kind of projects. The first one are the projects where people collect the data. So it's also called volunteer sensing. People are sensors. And this is most of the time with smartphone apps at this point, but also, as I said, with sensors and other gadgets. Just one example for all, because it's very famous, just also look at the numbers. This is iNaturalist, and this is studies on biodiversity, and this is like a series of projects that have all to do with people going out during a walk, during a stroll, and take pictures. Can be of flowers, of plants, or insects, of animals, every kind of biodiversity. These data go in the International Biodiversity Facility, which is open data and accessible to all researchers. Second group of projects are the one where people perform data analysis on existing data. So the first group, they were going out collecting data. In this case, they analyze the data, and these projects usually happen with the web, via web interface. There are many platforms that provide this kind of projects, and citizens can do anything from image recognition, image tagging, translation, transcription of documents, really every kind, mapping, every kind of activity. Again, just one example, I really go back to the past, to very famous citizen science projects. This is Galaxy Zoo. This was a PhD student in astronomy that was tasked for his PhD thesis to analyze, I don't know how many hundreds of thousands of images from telescopes, and he basically gave that to the crowd. And people were looking at these beautiful images of galaxies from telescopes and helping with the classification. Third group is volunteer computing. As I said before, this may look some like very little activity on the side of the citizens. Simply you download a piece of software, and so whenever you don't use your tablet, your computer, your smartphone even, the CPU is used for simulation and modeling. It's pretty niche, extremely powerful, and really coming back, big times because of AI. One example, again, we are at CERN, LHC at home, you may have heard about it. Again, you donate your computing time to basically help the experiments and also the tuning of the machine. Very briefly, which are the benefits? I think for science they are pretty obvious. We are talking about comparing your typical research group, which is, I don't know, a few researchers, one or two professors, a few PhD students, versus potentially everybody out there can help you with your research, that can be part of your research. So resource optimization, a lot of data from a very vast geographical area, basically the globe, and for very long periods of times as well. Also, very important is the access to certain specific knowledge of certain communities, like indigenous communities, but also, for instance, there are a lot of citizen science in health, and there what you're looking for is maybe the knowledge and the expertise of patients or family of patients for certain diseases. So for science is very obvious, but for society as well is really becoming more and more apparent the benefits the citizen science can do in terms of education, scientific literacy, the democratization of science. Of course, you are really opening up a field that has always been very close and very limited to certain people. Empowering communities. This is communities with this data not only touch firsthand issues that are very close to them, they may have heard about, now they are collecting data, now they are seeing that, and this empowers them, and also, and very important, it causes a change in attitudes. So you really see the change of behaviors in the case of plastic is really very obvious. And last but not least, there is a lot of policy making that increasingly takes very seriously the data provided by citizens. And again, they have to be done in a certain way, they have to be produced in a certain way, but they have been used and they can be used for decision making and policy making. So we are moving now, focusing on plastic finally, but at least now we know what we are talking about. So we are talking about researchers, citizens, trying to answer to a scientific question. And in the case of plastic pollution, basically the scientific question is trying to understand the presence, the abundance, the distribution, and the sources of plastic pollution. So those are basically the goal and can be on the beaches, on the water, on the river, on the lakes. And in order to do this, people do a lot of activities that, again, very generally speaking, there are a lot of beach cleanups, people going to the beach, collecting and categorizing whatever they find there, litter pickups, litter classification, diving. There is a lot of citizen science done by people diving and really collecting litter or plastic in the water column. Recycling drives, that means basically is like ways to really try to convince people and involve people into recycling, and waste monitoring. And these kind of activities, of course, produce data that, and also images and data to be analyzed. And these have to do, well, it's useless to repeat that, but about all of the information about the constituency of the pollution, where it is, hotspot, plastic ingested by biota, that's another one, and waste management. So very much related, the kind of data and the kind of activities. And we will look now just at some of the projects. There are a lot of them. Really, just Google citizen science plastic pollution. You will see a lot of them. So I will just mention a few of them that go through like the main activities as I just presented. So the first one is the Australian Marine Debris Initiative. I am mentioning this also because it's probably one of the most famous one. Citizens are basically monitoring plastic pollution all over the coast of Australia. I mean, they honestly kind of adopted each city, you know, the cost, the close by cost, and they are providing data. Some of the numbers there, not all the citizen science projects have these impressive numbers, but this is one of the ones that is really quite big. And again, it's like schools, it's companies, it's local administrations, local government, really every kind of players and stakeholder in society. And the good thing of this project, another reason why it's very famous, is because the government at this point is using this database as the official database, the official source of information on plastic pollution in Australia. So this is obviously you know, a big deal. So that was not using an app, that was not like using a sensor, it was like people going to the beach. There are a lot of other projects that use apps. This is just an example, this debris tracker, and where you have a nice iPhone, you know, app, and you are around, you are on the beach, you take pictures, you classify, and again, a lot of success, a lot of data. I think what I find particularly interesting here is actually Morgan Stanley, the National Geographic. So you have increasingly like players from business, from the private sector that are behind these projects. I don't know, we can discuss about this, but at the moment what I would say is that I think it is very positive that this kind of initiatives are really backed up increasingly from every player of society, and not only academia, because academia at the end of the story is not always so rich. So we have seen an example of like people collecting, one with a smartphone. Now this is an example of the project that I mentioned before where people do analysis. So Plastic Tide is a project that, as the one that Gianluca mentioned and that we did with Polarquest, is starting from drone images. So you take images of the beaches with a drone, you use the AI to basically try to classify whatever you see. However, you probably know that also the data set that is used to teach AI how to recognize plastic has to be what we call it like a clean data set. So somebody has to look at the images and make sure that what you're classifying is actually plastic, and then feed those images to the AI algorithm to actually learn how to recognize plastic. So who is doing this job? Citizens in this case. So citizens basically work as the cleaner of the data, or the one basically prepare the set of data that then will teach AI. And this is just an example. This is a screenshot from their tutorial. This project, you may wonder, one of the typical questions is, how can you trust citizens on a topic they know nothing about versus scientists? You know, they've been studying for years. And yeah, I mean, there are ways of doing things to actually make sure that your data, the data produced by the citizens, are quality data. One of these ways are tutorials. And this is just an image, a screenshot from the tutorial of the Plastic Tide. And you see that really, you know, they explain to you what you have to look for, and you know, what is plastic, what is not plastic. And then just, you know, since I'm talking about this, of course, this image will not be shown to just one person. So you never trust one citizen. You trust 10 citizens, 20 citizens. So you really have a statistic on your side. You show the same image to a certain number of people, then you have your 90 distribution and your answer. And I will finish this presentation talking about something else. Well, it's not something else. It's probably, I mean, you are all here, you must be related to the UN, and I bet you all know the Sustainable Development Goals. And this kind of data that I've been talking about, that in UN language, they're not called citizen science data, they are called citizen-generated data, because they actually include citizen science, but other kind of data from, you know, mobile networks, satellites, and things like that. But there is this effort going on since years by now to really try to fill the gap in data for the Sustainable Development Goals with citizen-generated data, so with data from citizen science. Because everybody realizes how powerful this is. Citizens are everywhere. They could really monitor, they could really provide information. So we have really been trying to build this connection between the two communities. And this is like an amazing example that happens to be about plastic pollution. So it happens to be about, actually is goal 14, but is a target 14.1.1, which is plastic pollution, the index of plastic pollution. And among all the countries, the first one who took this very seriously was Ghana. And they did an amazing job in trying to combine satellite images, artificial intelligence, and ground truthing by citizen science to actually provide the data to report to the UN about the Ghana data on plastic pollution. So this was an amazing success, and just, you know, I think I've been very positive in this presentation in the sense that it may seem as something straightforward, something, you know, easy to do. It is. However, if you want to reach this kind of results, like your data of your project being used by a country to report to the UN, then you have to do things really in a proper way. And this is the way they did it in Ghana. First of all, you have to find the right partners. Not only you need citizens, local citizen science groups, you also need the government. You need the statistical office of your country. They are really keen, they are statisticians. I don't know if you know any statisticians. They are very keen about how you get your data, you know, all of the quality and everything. You have to have them on board. You have to have citizen science on board, and you have to have UNEP on board because they are the custodian of these goals and target. But they all together work, they looked at what is out there, at the global methodology of the existing databases, and they actually managed to integrate all of that and to have it validated by the National Statistical Office. So a big success that is ready there to be copied by other countries and also, of course, for other SDGs goals and target. And I'm stopping here. Thank you very much.
Thank you, Rosy. We have time for questions. Please. Say your name.
Thank you. Boris Engelson, a journalist freelance. I have two remarks which can be turned into questions, one on citizen science and one on green science. Citizen science, the two modern science have started with citizens before the academia. Informatics, at least microinformatics in a garage in California, to mention the myth, and ecology. So how do you explain that citizens were able to invent modern microinformatics, but have never had significant contribution in mathematics, which requires just a pencil and a piece of paper? This is a paradox, and I have been looking for an answer to that paradox. You are the person who will fix the paradox. The second one is that, is that ecology is born outside academia, from citizens as a challenge to academia. Greenpeace, the green parties were challenging experts and academia. Not exactly, but basically, and they had to educate academia. How do you react to the second paragraph?
So go ahead with the second one.
Okay, the second one, Rachel Carson is the first ecologist. She was a marine biologist, and she wrote a book about the sea, the need for ecology, which is the manifesto of ecology. She was a marine biologist, and she is considered the founder of modern ecology that is science-based. Then the rest... That's the distortion of it. So the real ecologists are those with a scientific base who can say and assess the situation exactly as it is. At the time, her colleague were considering the sea as a place where you could dump. If you read our article on Springer about plastic pollution in the Arctic, we have an introduction on the birth of marine ecology, and Rachel Carson, which is also considered not just a marine ecologist, but the first ecologist on the planet, at a time where science was considering the sea as something where you could dump anything and nothing would happen. But also it was a time where we were much less on this planet, much less people, and we were producing much less, especially we were not producing plastic. Not sure. I don't know. There is on agriculture. There is a long debate. We will not dwell on that.
He was there.
Yeah. Okay.
And
the
about
first question.
Yeah. I mean, again, for the first question, I think the term scientist was invented like sometimes around 1835 or 1837. Before that, you know, the scientist did not exist as a job. So everything that was done before that was citizen science. And there was some mathematics as well. There was Galileo, there was, I don't know, Darwin,
Newton.
There was Newton. So they did it with a pen and pencil. They were citizens with a passion. I mean, I may agree with you that nowadays that passion may not, with a piece of paper and a pen, bring you to the same level of academic scientists that have, you know, big
If you're
computer.
a theorist, yes.
But yeah, theorists, I think
mathematicians
that
also.
actually, yeah, from CERN you can tell us
Yeah.
if theorists work with paper and pen or the computer.
Okay. There's a question down there. Thank you in any case, Boris.
Hi, this is Bilge from Turkey, and thank you for your valuable remarks. So my question is about, are the citizens, do they get feedback when their products are utilized? I mean, in some cases I saw that the task is simple, like tagging an object, whether it's plastic or not. But in the more complex versions, such as creating a data set, are there any specific descriptions that we exactly need that, etc.?
So, I mean, to answer to your question, yeah, there are always explanations. I mean, every time you're asked to do something, you know, there is a tutorial, you may have people helping you on the field. There are many different ways. But I think that the more interesting aspect to your question is, what are we giving back? You know, how are the citizens getting any value? I said at the beginning of my presentation, these projects have to be beneficial for both communities. So for scientists, it's obvious, they get their beautiful, wonderful data. What about the citizens? And so citizen science, usually you don't pay citizens, so there is no money involved. There are exceptions to this rule, but like I would say that 99% there are no money involved. So you have to give back to citizens in other ways. And the way you give back basically is by knowing their motivation to participate. And there are a lot of studies on that. People participate because they want to be part of something bigger than them. They want to do science. They want to learn. They want to get in contact with scientists. We are at CERN, you know, we are dealing with scientists every day. We don't think it's something amazing. There are a lot of people that do think that talking to an expert in their field, oh my God, I mean, that's a unique opportunity. So these are all ways that you have to give back. And these projects usually have forums where you put people not only in contact between themselves, and they love that, you know, like they belong to the same, you know, group of people that are very passionate about a certain subject, but you also put them in contact with the expert, with the researchers. And
also have publications.
And they also have publications. I mean, this is something that you can give, you can offer, especially depending on really how much the citizens have been contributing. But you know, citizens, honestly, my experience, they don't care about the scientific publication. I mean, they don't even know what it is. That's, you know, valuable money if you are a scientist, but if you are a member of the general public, you don't really care about the scientific publication. You care much more if your project is featured at the radio or in like a local newspaper. So you really have to, you know, try to satisfy them in any way that they want, that you can. And usually you ask. I mean, it's really a communication between the two communities on how to really get the best out of the project for everybody.
One more question down there. Can you pass it behind you?
Thank you. Hi, I'm Catherine from the University of Georgia, and we run the Marine Debris Tracker project at UGA. I think one of the particular challenges with plastic pollution in citizen science is that unlike taking pictures of butterflies, it can be kind of discouraging for participants to realize the scale of the problem and how big it is to address. So I would love to hear from a communications perspective how you've really framed the impact that citizen science are making by participating.
So one topic that I didn't touch at all, and thank you very much for this question, is like citizens' engagement. You know, you may think, and actually most of the time scientists do think, that here they come with their project and citizens have like nothing better to do than just, you know, join your project, and they all expect the kind of numbers that you saw, you know, hundreds of thousands of people. So that is not the case, first of all, and getting citizens and keeping citizens is a job. It's called community management, and you need in your project, you know, somebody that will take on this task. And the idea is, I mean, there are very few general rules because the participants really depend from the kind of projects you are doing. But let's say, in general, depending on your project, you may identify people that have an interest, okay? Association, NGOs that have an interest. So you think about it. Who can be interested in my project? Okay, you identify them. Where are them? Do not expect them to come to you. You have to go to them. And you have to go, again, to local association. Lately we are using a lot Facebook groups. It's amazing. There are Facebook groups for everything out there. So you really find every kind of people. You go, you kind of convince them to participate by showing very clearly what is the value of their participation and the value of the results that they will obtain. So they come and they join, and most of the time you will never see them again. You know, depends, maybe your project is boring or maybe not, and they will come back. However, the community manager has to be there and run behind these people and get them back. And the way you do it, again, is just making sure that you give back what they are expecting. Can be knowledge, can be, you know, networking, can be simply knowing, you know, that their data are being used for something very meaningful. Or sometimes, who mentioned before a thanks, you know, just, you know, thank you, you know, you contributed your 10th data, your 100th data. So, and this is all this community management, you know, arts and science that is really time consuming and really important in a community, in a citizen science project.
Thank you. You can continue talking to Rosy during the coffee. We just move on to the next presentation, which takes us to the second part of our main subject, not by importance, just second like that in chronologically. So I have with me Sioni Summer, who is a physicist at the Compact Muon Solenoid experiment, the CMS experiment at the Large Hadron Collider. who is also a member of the ETHZ project, and he'll tell us more about this project, which is a CERN, CMS, and European funded project with various partners, of which CERN is one part. I'll let you explain everything about EdgeSpace. Thank you, Shirley.
Thanks for the introduction. I'll just wait for the slides to appear. Looks like it. Okay, great. Yeah, I'll present about the EdgeSpace project. So I'll give also the connection to CERN. So I'm a physicist at CERN, and in my day job here, I'm using machine learning technology, AI technology for the LHC experiments, in particular CMS. And there our task is to select interesting physics events effectively and quickly. And for this task, we've developed our own solutions, and I'll explain why a bit later in the talk, where we have some specific targets of very fast and low power selections. And we've adapted this technology for use in the EdgeSpace project to Earth observation satellites, where there's a similar kind of problem that interesting events, interesting objects on the surface might be rare compared to the majority of the images that are collected by the satellite. And we can use machine learning or artificial intelligence on board the satellite to select only the relevant data up there and only send to the surface the relevant data. So the project is partly a technology demonstrator for that type of approach, and also a project specifically delivering some tools for monitoring plastics pollution in the oceans. So in this specific talk, I'll focus on the CERN contribution to the technology, and also on the challenge of the plastics pollution, which is largely the contribution of the National Technical University of Athens, so I thank them for some material that I've used. The project is a consortium with 4 different partners that touch on all of the important aspects of getting a project like this on board to a satellite. So that's us at CERN with the technology for running this artificial intelligence quickly. Agenium Space, who are a French company that target machine learning solutions on board Earth observation satellites. Endurosat, who actually manufacture and operate satellites. And the National Technical University of Athens that I mentioned, that are particularly involved in the plastics pollution problem. So like I said, we've been, our target is partly to monitor the plastics pollution in the oceans using Earth observation satellites, and I'll explain a bit the challenge of doing so. So our aim is kind of threefold. There's the demonstration of this in-orbit satellite monitoring of plastics pollution with a viable neural network, artificial intelligence running on a real satellite with the capability of identifying plastics pollution. It's also this technology demonstration about using our CERN technology for fast AI for onboard satellite processing, which could be adapted or adopted for other types of object identification problems. And also there's an aspect of improving European technology sovereignty, looking specifically at European device manufacturers. So a bit of the challenge with Earth observation satellites and processing. The approach today for a satellite mission is typically to downlink all of the data that's collected. So we're talking in this case about satellites with cameras that are facing the surface of the Earth. And typically when the satellite passes over a receiving station, it will be sending all of the images it's captured in the last run downlinked. But over time, the sensors that are used, these cameras, get higher and higher spatial resolution and spectral resolution. The cost of launching and operating satellite missions gets cheaper, especially in the context of nanosats or CubeSats. And this creates this increasing demand for downlink capacity and downstream processing, which is a data handling challenge and also a cost challenge that's factored into the cost of the mission. And also in this context of nanosats and CubeSats, one specific mission might be only looking for one specific type of object on the surface. So for instance, you could have, imagine a satellite or a constellation of satellites specifically tasked with monitoring plastics pollution, but of course it will capture images of all kinds of other objects in the process. And this traditional approach of downlinking all of the images implies sending a lot of useless data down to the Earth's surface. So in the project, we're looking to, through this technology demonstration, shift the processing onto the electronics of the satellite itself so that we can send only the relevant data back to the Earth's surface. And there are some technological challenges that need to be overcome to realize this, and that's what we're looking to solve in this project. So here's the kind of schema of the project and a bit the different responsibilities of the different parties. Maybe I'll use the mouse pointer to highlight. So we start kind of on the top left over here that we've collected some data set of images, including some plastics pollution in the oceans. Our collaborators at the National Technical University of Athens train artificial intelligence neural networks to identify the plastics pollution. The Agenium space, through a process called distillation that I'll explain, shrink that artificial intelligence down to a size that is compatible with the kind of hardware that we have on the satellite. We can then use the CERN technology to map that specific artificial intelligence to the hardware we have on the specific satellite, and then EnduroSat take care of actually monitoring, integrating, and the operation of the satellite itself. And then we can kind of close this loop where we are then able to monitor and collect new images of this plastics pollution using the solution. So then I'll get into some of the specifics of these kind of 4 different aspects. So the first of these, it's probably the most interesting for specifically the plastics pollution monitoring aspect, is this data set and neural network artificial intelligence that's been curated by the Athens group. So there's a data set here called MADOS, standing for Marine Debris and Oil Spill Data Set. And it's an open access data set. So here, not labeled with citizen science, but talking about open science. So it's freely available to access all of these labeled images. It includes 15 different classes or categories, including oil spills and plastic debris. And it's based on multispectral satellite data collected by the Sentinel-2 satellite. They also provide a novel AI framework named MARINEXT, which actually identifies the plastics pollution in those images. So I put some links in the slides. I think these are available through the event webpage, or you can kind of make a note of them now or kind of Google this MADOS dataset. But these images, of which there are a few examples on the slide, are available, including the annotations. And also the neural networks that have been prepared. So some more specifics about the actual dataset. It has 174 scenes and 47 tiles captured in this date range, covering 22 different countries that there's a graphic of on the next slide. The text might be a bit too small to read about the specific categories, but right at the top there is marine debris, which is including floating plastics and other human-made debris. But it also covers other categories of objects that one would find in ocean images, so oil spill, different types of algae or seaweed, different types of man-made material like organic material or ships, several different categories of different types of water, and some other categories. And this is labeled at the level of individual pixels in the image. So for every 1.5 by 1.5 meter pixel, it's labeled which of these categories it belongs to, done work carried out by the team here. And in the context of this project, the team has extended the existing dataset with more observations in specific regions and expanded the number of categories that are included. So that's a quick overview of the regions that are covered in the dataset. And then here, the MARINEXT artificial intelligence, which was their solution for identifying the marine debris or all of those categories in the images. So I won't talk about it in detail, but I want to focus on the part that the task we're solving here in the sense of the AI is called segmentation. So that means taking an image of pixels, and for every pixel, identifying which category that pixel corresponds to. And it's done with this specific type of neural network here that I won't describe. But in the end, they take a kind of majority voting across multiple different sub-neural networks. And the idea is that we can bring this to the satellite itself, identify these pixels of marine debris, and use that to decide whether the image should be downlinked or not. Here's then a bit more concrete view to give you an idea of how well this task can be solved. So there's some example images highlighting the capability of identifying the different categories. So you have each row is one different scene, and then each column is the labeling from a different method, where the right-hand side is the best performing MariNext model. And so you see the color coding of the different labels at the bottom. So of course on the left-hand side you have the raw image, and then the others are the different labels. So in particular here, for instance, in red is the identified marine debris. And these examples are curated to highlight a couple of the different categories that can be seen. So that's the creation of a data set, including lots of examples of marine debris, and the creation of a neural network that can identify them. So I mentioned previously that we need to do a process of shrinking that neural network to something that's compatible with the limited hardware that we have on our satellite. So that's the role of Agenium Space in this project, and they use a technique that's called knowledge distillation to shrink the neural network. So what I described, that MariNext model, is what we call in this context a teacher neural network. So it's large, it's high performance, it can perform the task well, but it's too big for the hardware that we have in space. But we use the predictions that it can make to train a smaller neural network that we call a student, and this is what we target for the satellite. And we find with this approach, we can achieve better overall performance than just starting from the student itself and trying to train that directly on the images. So that's the approach, and that's some specific software and methodology that this partner puts in place for this project, so that they can hand off this student model that we in the CERN team can then target for the satellite hardware. So the next part of mapping one of these neural networks to be able to put it in orbit is to target the specific type of computing hardware that we have on the satellite. Space is a challenging environment for operating electronics and computing. So we need to have a low power usage that's limited by the availability of whichever platform we're using, and it's shared across multiple satellite systems. So in our case, the budget is something like 10 watts. It's also a radiation environment where solar radiation can damage equipment and also can cause errors in the computation. And this needs to be accounted for in the design of the electronics. So we use a specific type of compute hardware called field programmable gate arrays in satellites often. These are digital circuits that can be reconfigured, and they can also achieve high performance for computing and good power efficiency. And they're also used extensively throughout CERN, so we have lots of expertise there, including using them for artificial intelligence. So now I take a small diversion to explain the CERN aspect of the technology that we're targeting here, and explain what's our relevance in that space of selecting data on board Earth observation satellites. So we actually have a similar type of problem at the Large Hadron Collider experiments, where we collide the proton beams 40 million times per second. That produces in our detectors extreme data rates of hundreds of terabits per second, where an event is an example like is shown in the image here. This is all of the particles measured by the detector from one collision, and then reconstructed with software to be able to create the image. But we produce a new set of particles like this 40 million times per second. But we know from the physics involved that most of these collisions don't produce exciting new particles, for instance, for finding the Higgs boson. So with 40 million collisions per second, we produce something like 10 Higgs bosons per second. So we use a system called a trigger to throw away those events that we don't need to use for the analysis later on. Those that we can identify as quickly, as not interesting for the analysis. And that helps us reduce the data rate down to manageable levels. And we increasingly use machine learning, AI, to perform that data selection. So we solve this with a kind of hardware system. You'll get maybe some sense of this during one of the visits later, seeing the above ground part of this. So the left-hand side of this cartoon is underground. There's the actual detector 100 meters below ground, and then a whole room of custom electronics next to it that does this real-time filtering. And this is a bit like our satellite and its onboard processing. The role of this system is to process all of the data that comes from the experiment, make a very rapid decision about what's relevant or not, using those same type of FPGA processors that we have available on the satellite, and we use machine learning to make some of those selections. The data that is selected by that system is then passed through more stages of filtering, but eventually it's made available to physics analyzers for performing their physics studies. And for solving using machine learning in this system, we've developed some of our own tools. So there's this project, High-Level Synthesis for Machine Learning, which is a specific technology used for putting artificial intelligence into this type of compute that we have in the trigger system and on board the satellite. So it's an open source software. It can be freely downloaded. Users, which can be domain scientists, so they could be physicists at CERN, they could be plastics pollution experts that have created a data set, but it covers quite a lot of different domains. Users will prepare their neural network. They'll train a model on a data set. Then they can enter the open source software tool and produce different types of output that we can use for these kind of custom computing applications. So that can be compute acceleration, that can be searching for new types of physics, and we can also even produce some custom silicon that we can put back into our particle detectors. One of the key ingredients of the solution here, why we invented our own tools rather than using off-the-shelf AI solutions, is to achieve this extremely high performance. So the solution is what's called a data flow architecture. A neural network is typically composed of different layers, and having multiple layers in one neural network. And in this data flow architecture, one layer maps onto an independent compute unit in the chip. So this means that the computing is fully inside the chip. We don't communicate with the outside world too much, which is really great for high performance and power efficiency, but it does limit the size of the neural network that we can put into the chip. So there's an example here where we have this data set of handwritten digits. This is a neural network which is color-coded, where each layer has a different color. And then this is a view inside the circuit that we produce with the tool, where there's the same color coding applied to the different boxes. So you can see this pink unit here is this first layer, and this green unit at the end is the last layer. So the data kind of moves around the chip. And for us in the LHC experiments, we can get extremely fast AI predictions, but it's also quite useful for very low power machine learning, which is kind of the use case for the onboard satellite processing. So that's the technology we're using for the project and why we're using it inside CERN. What we've done in the context of the EdgeSpace project is to target those neural networks provided after the knowledge distillation, in this case on a data set of cloud segmentation. So not yet working with the full data set that I showed, but this is a kind of Earth observation benchmark problem, since at any one time 50% of the Earth's surface is covered by cloud, and any image that's obscured by clouds is not usable for surface object detection. So it's a kind of easy first filtering that one can try. So here we take this data set of images and we perform this segmentation to label every pixel as cloud or not cloud. So in the example, you can see it's majority covered by cloud and a bit of surface peeking through. And on the right-hand side, you can see the prediction that comes out of the neural network correspondingly. So within the project, the team of developers here at CERN has worked to improve the state of the art that we could achieve with that tool in terms of AI model performance, allowing us to put neural networks 10 times larger than we could previously into the same device that we have on the satellite. And the team also contributed to various bits of the ecosystem of this open source high-performance machine learning. And now we can put this cloud segmentation neural network through our tool, run it in the right hardware, and measure the performance. So this is what we get after doing that. We load this cloud segmentation neural network onto this FPGA board, which is quite representative of what we will have on the satellite, using both the CERN tool, HLS4ML, and using a commercial tool from the manufacturer of the board. And then we run some predictions on some images from that data set and measure the performance. So we care about especially the frame rate, how many images per second can we make predictions on, the power consumption on the hardware, since I mentioned it's limited what we'll have available on the satellite. And then this metric that's kind of an aggregation of the two is the pixels per second per watt, where the CERN technology solution is 24 times improved against the commercial solution on that important metric. And this is with a particular size of neural network. The team's still working to deploy even larger ones that would get ultimately better performance for identifying the marine debris. So that's all of the technology related to putting artificial intelligence into those type of processes for Earth observation satellites, which is the CERN role in this project. The other aspect is actually having a satellite. So this is the responsibility of Endurosat here. They launched their project Balkan 1 in January. So this will be used as the basis for the in-orbit demonstration of the plastics pollution. They've started collecting data and calibrating and so on. And also, as part of the idea of reducing the downlink needs, the mission will be capable of sending a beacon, like an alert, just to say there is an object of interest at these coordinates, rather than downlinking all of the images. And that's kind of joined up in some software platform run by Endurosat. So that brings me to the conclusion. So, ETHZ project is about deploying artificial intelligence for Earth observation on satellites and identifying marine debris, plastics pollution, in real time. The objectives are this technology demonstration to reduce downlink bandwidth requirements by identifying interesting objects already on board the satellite, targeting plastics pollution through this curation of a specific data set and AI models, and using the CERN technology to achieve higher performance in terms of power efficiency on the satellite. I'll finish there. Thanks.
Thanks a lot for this in-depth dive into the science behind EdgeSpace. Any questions? We have time for a few questions. Nobody dares? No, I just wanted to ask, when is it going to be? You say the project finishes in 2026. You will have a demonstrator ready, and then what's next?
Yeah, that's a great question. So the project is finishing at the end of 2026. So we're working towards our various milestones, but we have the satellite is in orbit already. So it's under that process of being calibrated. So during 2026, I think we expect to be doing the kind of demonstration.
Collecting data.
Yeah, exactly. Then in terms of what next, in terms of consuming the data, using it for specific purposes, and maybe adapting the technology for cases other than plastics pollution monitoring, which could cover, for instance, wildfire detection. This is sort of ongoing, and I mean, we're open to discussions here, basically, for identifying specific use cases for the data.
Yeah, I think in the implementation of the treaty, this monitoring phase will be very important. And if it can be done so efficiently by satellite, that would be a very important tool for the plastic treaty implementation and monitoring. Any comments, reaction, questions? Is anybody? Yes.
Hi, my name is Justin. I'm from the Zhonghua Institution for Economic Research in Taiwan. So just a question about the analysis of this plastic. So how small of the plastic can your image analyze in? Can it be a single piece, or it has to be a cluster of plastic?
Yeah, so this is somehow inherent to the satellite platform, I suppose, that the pixel size of the camera mapped to the surface of the Earth is 1.5 by 1.5 meters. So that gives you some idea of the scale. We're looking at patches, basically. I think even it would have to be multiple pixels together in a kind of patch to be able to identify it reliably. So yeah, that's the kind of scale that we're talking about.
Thank you for the question.
And I'll hang around during the coffee break and the networking. Yeah. I can answer questions there.
So we are having a coffee break in the kitchen. Just follow us. So just next door. And then people who are signed up for the visit, it will be me and Rita. Rita, she's there. So Rita is also a part of the EDGE Space project. I would like to thank all the speakers, the IdeaSquare support team, and our technical team, because we had a lot of challenges, especially at the beginning with sound. We are streaming on YouTube, we have people on Zoom, we have the screen here, so it wasn't super easy, but now it's been working impeccably. Thank you very much, Ron and Piotr, and thanks Stefano Aliani, Gianluca Casagrande, Rosy Mondardini, Sioni Summers, and thank you for attending this meeting. It will be available on the YouTube channel immediately as we stop streaming. You can follow and catch up if you haven't followed from the beginning. Thanks a lot.